Section 15.11, Entropy. So in general, irreversible processes cause us to lose some, but not necessarily all of our ability to do work. This partial loss can be expressed in terms of a concept called entropy. Another way to think of entropy is increased disorder. But here we're going to focus primarily on the loss of ability to do work. So to introduce the idea of entropy, let's first remember our Carnot engine, that we had this relationship between QC over QH is equal to TC over TH, the ratio of the cold to the hot heat versus the temperatures is equal. And we could rearrange it to be QC over TC is equal to QH over TH. We're going to use this type of quantity for entropy. We're going to say the change in entropy is equal to Q divided by the temperature. So entropy we're going to use a capital S for. So delta S, that's our change in entropy, is equal to the heat divided by the temperature in Kelvin. And we have a subscript here for R, that this is an equation that applies to reversible processes. So a Carnot engine is an example of something that is reversible. It can operate in either direction. Let's actually try this out with a Carnot engine. So we'll do that in just a moment. First, I want to highlight entropy like internal energy, delta U, that we've seen before. It's a function of the state of the system. So it just depends on, if you look at the system, like a gas, like what is its state right now? What's its pressure, volume, temperature, right? We can know the state, and it doesn't depend on what process we use to get there. That will be useful in a moment. Now, if we consider the entropy change of a Carnot engine, the entropy of the hot reservoir decreases, and the entropy of the cold reservoir increases. The hot reservoir is giving up some of its heat, so it loses entropy, versus the cold reservoir is taking in more heat, so that increases the disorder. That's a gain in entropy. So that's a useful thing to note in this general equation for entropy, is that the Q is going to have a sign here. We're no longer dealing with the magnitude of the heat, right? So we're going to put it as positive anytime heat enters the reservoir, or heat enters a reservoir. And then it's going to be negative anytime heat is leaving the reservoir. And so this is illustrated with our Carnot engine, right? The entropy is leaving the hot reservoir. The heat's leaving it, so that's the negative sign there. The cold reservoir is having heat enter, so that's a positive sign. But we know that the ratio QC over TC, that's equal to QH over TH. So the net change in entropy for a Carnot engine is 0. This highlights a really important principle, that reversible processes do not alter the entropy of the universe. The overall entropy of the universe stays the same. What about irreversible processes? We said that this equation works for reversible, but much of life is not reversible. What do we do then? Well, it's a bit more complex with an irreversible process. We don't know exactly how the entropy changes during the process. But we could imagine between the initial state and the final state, we know there's this irreversible process that spontaneously occurs. We could imagine a hypothetical reversible process that goes between the same initial and final states. And since entropy is a state variable, it only depends on those endpoints. This means that the change in entropy for our irreversible process must be the same as the change in entropy for our hypothetical reversible process. In other words, if we pretend that our reversible process is reversible, we can calculate the entropy. It's a little fancier than that, but that's effectively what we do. Let's try it out. So the entropy of the universe increases. The figure shows 1200 joules of heat spontaneously flowing through a copper rod from a hot reservoir at 650 Kelvin to a cold reservoir at 350 Kelvin. Determine the amount by which this process changes the entropy of the universe. All right, so we're looking for the change in entropy of the universe, right? It's not just the delta S of either one of them, but of the universe. What does this mean? Well, this means that we're going to have a change in entropy in the cold reservoir, as well as a change in entropy in the hot reservoir. And we're going to need to account for both of them, including with sign. So which one is going to be positive, which one's going to be negative? Well, note the heat is going into the cold reservoir. So because the heat is entering it, this one is one that we expect to be positive, times those quantities. And then for the hot reservoir, heat is leaving it. So that is actually a loss in entropy. So we expect a minus sign there. All right, and we know the entropy is equal to Q over T, right? That's our general equation. So for the hot reservoir, it'll be the heat leaving the hot reservoir with TH. Cold reservoir would be the heat going into the cold reservoir with the TC. So let's check out the actual calculation of it. All right, so we again have the cold reservoir, QC over TC, minus the change in entropy of the hot reservoir, QH over TH. Now notice in this case, because we don't have an engine in the middle, the QC and QH have the same magnitude, right? It's the same amount of spontaneous heat flow from one to the other, but the temperature on the bottom is different. So overall, our change in entropy comes out to positive 1.6 joules per Kelvin. And this is what you will see for any irreversible process, that overall the entropy of the universe will increase when you consider the entire universe, that is. We're not able to have the entropy decrease. You won't get a negative value on these calculations. So this introduces another way of looking at the second law, right? So because an irreversible process increases the entropy of the universe always, we can state the second law in terms of entropy. We can say the total entropy of the universe does not change when an reversible process occurs, like our Carnot engine, and it increases when an irreversible process occurs. In other words, entropy is only going to stay the same overall. That's the best we can do. There's no loss, but we're not going to lose entropy. And if it's an irreversible process, we're going to gain entropy. So we can look at the effect of these irreversible processes on the work that we can get out, how it can take away from our work available. So example 12, energy unavailable for doing work. Suppose that 1200 joules of heat is used as input for an engine under two different conditions as shown below. Determine the maximum amount of work that can be obtained for each case. So notice in the first case, we have our standard heat engine, a hot reservoir at 650 Kelvin. Then we have this input heat of 1200 joules that goes into a Carnot engine. We get some work out and some heat that's rejected. Second case, we have heat spontaneously flowing through this copper rod of 1200 joules, right, into the hot reservoir. So the hot reservoir is now at a lower temperature, but we still get 1200 joules going into the Carnot engine, and we get some work out and some rejected heat out. So how does that affect our work? Well, because we want the maximum amount of work for each case, that clues us in that we can use the Carnot equation. So we can look at the Carnot efficiency of each engine and then see how much work they can give us. Right, so the maximum amount of work is when the engine's a Carnot engine. So the Carnot engine efficiency is 1 minus Tc over Th. So for the first case, we have 150 Kelvin divided by 650 Kelvin. So it comes out to an efficiency of 77%. And we can calculate the work with the efficiency times the input heat. And so it comes out to work of 920 joules. Pretty good. In the second case, notice the temperature of our hot reservoir is now lower. So because that temperature has dropped, our efficiency drops as well down to 57%. We lose 20% of our efficiency. So the amount of work that comes out is now 680 joules, right? So this irreversible process of heat flowing through the copper rod causes some of the energy to become unavailable, right? If we take the difference between these, we'd find that there's 240 joules that is now unavailable for doing work. We get less work out because of that increase in entropy due to the copper rod. And so this highlights actually a nifty little equation that we can calculate the unavailable work with the temperature of the coldest reservoir times the overall change in entropy of the universe. So if we try it out with our numbers, the cold reservoir was at 150 Kelvin, and the change in entropy of the universe that we calculated for that copper rod in example 10 was that 1.6 joules per Kelvin, which, by the way, those are the units of entropy. It's heat over temperature, so joules per Kelvin. I'm being serious, not JK in here. It's J per K. All right, so if we multiply these two numbers together, guess what we get? 240 joules. We're able to calculate how much work is unavailable by using entropy. This is awesome. It's really cool to see how that plays out. And this is true for any irreversible process, that we are going to lose energy in this way. Reversible processes, they don't have the problem of having an increase in entropy, right? So they don't lose work available in the same way. So an example of a reversible process, if you have a block of ice, you can melt it into a puddle of water, and that will be an increase in entropy. It's less ordered here. But you could then freeze the block of ice again, and the entropy would decrease. And if you'd have the same change in entropy either way, so the overall entropy of the universe would not change for a reversible process like this. So you don't necessarily lose your work with such a process. All right, so there introduces entropy and another way to look at the second law of thermodynamics. And I mentioned there were 4 laws of thermodynamics. We got the 0th, 1st, and the 2nd. So there's one more. Section 15.12, the 3rd law of thermodynamics. The 3rd law of thermodynamics just says it is not possible to lower the temperature of any system to absolute 0 in a finite number of steps. In other words, it would take an infinite number of steps to reach absolute 0. And that's why we can't reach absolute 0, right? We can't take an infinite number of steps. And that's part of why engines can never reach 100% efficiency. Because unless the temperature of the cold reservoir is 0 Kelvin, there's going to be heat loss. So, 3rd law of thermodynamics brings it all together with showing that we cannot quite reach absolute 0 on any finite scales. And this brings us to the end of chapter 15, where we saw all 4 laws of thermodynamics working together.